Welcome. Friends, I'm so glad you're here, whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion. You found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the vast corridors of space where solar wind flows and ancient visitors carve temporary paths through the cosmic dark. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Beyond the orbit of Neptune, in the cold realm where sunlight becomes indistinguishable from starlight, something moves. It drifts with the patience of geological time. This visitor from another star system, carrying within its frozen heart the chemistry of a world that died before our sun was born. The object measures perhaps 2 kilometers across, small enough to fit inside a modest crater on the moon, yet massive enough to hold the gravitational memory of its journey across 40,000 years of interstellar darkness. Scientists will eventually designate it 3Y/Atlas, the third confirmed interstellar object to enter our solar system, following 1I/Oumuamua and 2I/Borisov. But for now, in this moment of approach, it remains nameless, unobserved. A wanderer whose only companions are cosmic rays and the faint pressure of photons from distant stars. Its surface, blackened by eons of radiation exposure, absorbs what little heat reaches it from our sun, barely enough to warm it above the temperature of liquid nitrogen. The visitor's composition tells the story of its origin: water ice mixed with carbon monoxide, methanol, and hydrogen sulfide, the frozen breath of a star that burned out when the Milky Way was younger and smaller than it is today. Unlike the comets born in our solar system's Oort cloud, this object carries isotopic signatures that mark it as fundamentally foreign. The ratios of heavy water to normal water, the abundance of certain organic compounds, the crystalline structure of its ices, all bear the fingerprint of stellar nucleosynthesis that occurred in a different corner of the galaxy. As it approaches, the visitor begins to feel the sun's influence in ways both subtle and profound. Solar photons, streaming outward at the speed of light, begin to warm its surface by fractions of a degree. This heating remains imperceptible to human senses, yet it marks the beginning of a transformation that will reshape a small portion of the space through which our planet moves. The first molecules of water vapor begin to sublimate from the darkest regions of the comet's surface, perhaps only a few thousand molecules per second, an amount so small it would not fog the smallest mirror. But the sun's influence extends far beyond mere heat and light. Streaming outward from our star at speeds approaching 400 miles per second flows the solar wind, a river of charged particles that fills all of interplanetary space with an invisible atmosphere of plasma, protons and electrons, accelerated by the sun's magnetic field and expelled from its corona. Create a sphere of influence called the heliosphere that extends far beyond the orbit of Pluto. This solar wind carries with it the sun's own magnetic field, frozen into the plasma like iron filings trapped in flowing water. The visitor encounters this solar wind while still beyond the orbit of Saturn. Though the interaction remains too weak to detect with current instruments, individual protons strike the comet's nucleus with the gentleness of snowflakes. Yet each impact deposits energy and begins the slow process of sputtering, the erosion of surface materials atom by atom. The comet's gravity, weak as it is, cannot hold these newly liberated particles, and they begin to form the faintest suggestion of a coma around the nucleus. Here lies the first irony of the visitor's journey. An object that has traveled for millennia through the absolute cold of interstellar space begins to warm and change precisely when it encounters what we consider to be empty vacuum. The space between planets, though emptier than any vacuum achieved in Earth's laboratories, nonetheless contains enough matter and energy to gradually transform our ancient guest. The solar wind's pressure remains nearly undetectable at these distances, roughly equivalent to the weight of a feather spread across an area the size of a football field. Yet this minuscule force acts continuously, without pause, beginning to shape the comet's emerging atmosphere in ways that will become significant as it approaches the inner solar system. The charged particles of the solar wind cannot easily penetrate the comet's neutral gas cloud, and so they begin to flow around it, like a stream dividing around a stone. This deflection of the solar wind represents the first measurable effect the visitor has on its environment. Instruments aboard spacecraft in the outer solar system might detect the faintest variation in the density and magnetic field strength of the solar wind as it flows past the approaching comet. The disturbance remains tiny, a deviation of perhaps 1 part in a million, but it marks the beginning of the visitor's temporary reshaping of local space. As the comet continues inward, past the orbits of Uranus and Jupiter, its rate of outgassing increases exponentially. What began as a few thousand molecules per second becomes millions, then billions. The coma grows from a few hundred kilometers across to several thousand, though it remains invisible to the naked eye and detectable only by the most sensitive astronomical instruments. The composition of this gas cloud reveals the comet's alien nature, isotope ratios and molecular structures that differ subtly but measurably from those found in solar system natives. The mystery deepens with each measurement. How did this object escape its parent star system? Was it ejected by gravitational interactions with giant planets? Or did the death of its parent star blast it into interstellar space? How many others like it wander between the stars, invisible and undetected? Current estimates suggest that interstellar space contains perhaps 1 trillion such objects within a few light-years of Earth, wanderers from dead or disrupted stellar systems, carrying samples of alien chemistry across the galaxy's spiral arms. The second irony emerges as telescopes begin to track the visitor's path, an object that formed in the disk of another star, perhaps billions of years ago, now serves as a probe of our own solar system's structure and dynamics. Its interaction with our sun's magnetic field and particle wind will reveal properties of the heliosphere that remain difficult to measure directly. In this sense, the interstellar visitor becomes an inadvertent scientific instrument, mapping the invisible architecture of space around our star. The third irony lies in the visitor's timing. It approaches during an era when human technology has finally become sophisticated enough to detect and study such objects. Had it arrived a century earlier, it would have passed through our solar system entirely unnoticed. Had it come a century later, our instruments might be so advanced that its passage would seem routine. Instead, it arrives at precisely the moment when its detection represents a triumph of astronomical technique and international cooperation. The visitor's approach continues with the inevitability of orbital mechanics and the patience of cosmic time. Each day brings it several million miles closer to the sun, and each day the solar wind grows denser and more energetic. The stage is set for a gentle collision between interstellar matter and the sun's domain, a meeting that will carve temporary corridors through the flowing plasma of the solar wind and leave traces detectable for years after the visitor departs. In the deep cold beyond Saturn's orbit, sublimation and plasma physics begin their slow dance of transformation, preparing for the more dramatic interactions that await as our ancient guest continues its journey toward the inner solar system. The solar wind flows outward from our star with the constancy of a river and the invisibility of time itself. At the distance where Saturn orbits, this stream of charged particles moves at roughly 400 kilometers per second, fast enough to circle Earth in less than 2 minutes, yet slow enough that it takes 4 days to travel from the Sun to this realm of ice and shadow. The wind carries within its flowing plasma the memory of solar storms that erupted from the sun's surface weeks earlier, magnetic field lines twisted and compressed by the star's rotation, frozen into the particle stream like fossils preserved in amber. This invisible architecture of space extends far beyond what early astronomers imagined when they coined the term solar wind. The flowing plasma creates a dynamic, three-dimensional structure that fills the entire solar system with magnetic field lines, electric currents, and pressure waves. Near Earth, the solar wind's density averages about 5 particles per cubic centimeter, still a far better vacuum than any laboratory can achieve, yet dense enough to power the aurora and compress our planet's magnetic field into a teardrop shape. The wind's composition reflects the sun's own atmospheric chemistry, roughly 95% protons and electrons, with small amounts of helium nuclei, oxygen ions, and trace elements forged in the stellar core. These particles stream outward at temperatures exceeding 1 million degrees, though the extreme thinness of the plasma means that a human hand extended into this furnace would freeze rather than burn. The apparent contradiction between temperature and coldness reveals the subtle distinction between the kinetic energy of individual particles and the bulk thermal properties of matter. As our interstellar visitor drifts inward from the outer reaches of the solar system, it encounters this solar wind at its most tenuous. Here, beyond Saturn's orbit, the particle density drops to less than 1 proton per cubic centimeter, and the magnetic field strength weakens to a few nanotesla, roughly 1/10,000th the strength of a refrigerator magnet. Yet even at these minimal levels, the solar wind begins to exert its influence on the approaching comet. The first interactions occur at the molecular level. Invisible to any current instrument, individual protons from the solar wind strike water molecules in the comet's emerging coma, imparting enough energy to break chemical bonds and liberate hydrogen atoms. These newly freed hydrogen atoms, electrically neutral and unaffected by magnetic fields, stream away from the comet in all directions, creating a vast but nearly undetectable cloud of atomic hydrogen that extends for millions of kilometers around the nucleus. This hydrogen cloud represents the comet's first significant modification of its local environment, while the atoms remain far too sparse to affect spacecraft or planetary motions. They begin to interact with the solar wind in subtle ways. Charge exchange reactions occur when fast-moving protons from the solar wind encounter slow-moving hydrogen atoms from the comet. The proton captures an electron from the hydrogen atom, becoming a fast-moving neutral hydrogen atom. While the original hydrogen atom becomes a slow-moving proton, the beauty of this process lies in its asymmetry. The fast-moving neutrals, no longer affected by the sun's magnetic field, continue outward in straight lines toward interstellar space. The slow-moving protons, however, become trapped by the magnetic field and begin to gyrate in small circles around the field lines. This exchange effectively removes energy from the solar wind while adding neutral particles to the interstellar medium, a microscopic example of the larger process by which our solar system gradually loses matter to the galaxy. Meanwhile, heavier molecules in the comet's coma, carbon monoxide, methanol, hydrogen sulfide, undergo their own transformations under solar wind bombardment. Ultraviolet photons from the distant sun break apart these molecules through photodissociation, creating a complex chemistry of radicals and ions that varies with the comet's distance from the star. The products of this chemistry drift away from the comet at speeds of a few kilometers per second, too slow to escape the solar wind's influence, but fast enough to create local variations in plasma density and composition. The mystery of the visitor's exact trajectory deepens as astronomers attempt to trace its path backward through the galaxy. Unlike solar system comets, whose orbits can be calculated with precision millions of years into the past, interstellar objects carry uncertainties that compound rapidly over cosmic timescales. Gravitational perturbations from passing stars, interactions with the galaxy's spiral density waves, and the gradual recession of the local group of galaxies all contribute to the difficulty of determining where and when this wanderer began its journey. Current calculations suggest the visitor originated from the direction of the constellation Lynx, possibly from a stellar system that formed and died when our galaxy was significantly younger. But stellar motion over millions of years makes such determinations increasingly speculative. The comet might have been wandering for 1 billion years, passing through hundreds of stellar encounters, gradually modified by cosmic ray bombardment and the changing magnetic fields of interstellar space. The first irony of the solar wind's interaction with our visitor becomes apparent through careful measurement. The very process that makes the comet detectable to Earth-based telescopes also begins to destroy it. Each molecule that sublimates from the nucleus and ionizes in the solar wind represents a permanent loss of mass. Over the months of the comet's passage through the inner solar system, it will lose perhaps 1 million tons of material, a negligible fraction of its total mass, yet enough to leave a permanent trail of debris in interplanetary space. The second irony lies in the solar wind's dual nature as both destroyer and revealer. While the plasma bombardment gradually erodes the comet's surface, it also liberates previously hidden materials from the nucleus interior, allowing spectroscopic analysis of ices and organics that formed around another star billions of years ago. The comet's destruction becomes a form of archaeological excavation, revealing the chemistry and physics of stellar systems that no longer exist. The third irony emerges from the scales involved. An object 2 kilometers across creates disturbances in the solar wind that extend across millions of kilometers of space, like a pebble dropped into a vast ocean. The visitor's gravitational and electromagnetic influence propagates far beyond its physical boundaries, demonstrating how even small masses can reshape the flow of plasma on planetary scales. As the comet continues its approach toward Jupiter's orbit, the solar wind density doubles, then doubles again. The particle bombardment intensifies, and the rate of molecular dissociation accelerates. What began as gentle sputtering of surface materials evolves toward the more dramatic outgassing that will characterize the visitor's passage through the inner solar system. The flowing plasma of the solar wind, seemingly uniform and unchanging, begins to develop local variations in density, temperature, and magnetic field orientation as it encounters the growing obstacle of the comet's atmosphere. These variations, measured in percentages rather than absolute values, nonetheless represent the first significant modification the visitor makes to the large-scale structure of interplanetary space. In the cold realm beyond Jupiter, where sunlight provides less warmth than a candle flame, the ancient chemistry of a dead stellar system begins to awaken under bombardment by particles from our young and active star. Between Jupiter's orbit and the asteroid belt, where the solar wind has thickened to roughly twice its outer system density, the first measurable contact occurs between our interstellar visitor and the sun's flowing plasma. This interaction unfolds not as a collision in any conventional sense, but as a gradual interpenetration of 2 fundamentally different forms of matter: the ancient, neutral gases sublimating from the comet's nucleus, and the young, ionized particles streaming outward from our star's corona. The physics of this encounter operate on scales both vast and microscopic. Individual molecules of water vapor, carbon monoxide, and methanol drift away from the comet's nucleus at speeds of perhaps half a kilometer per second, roughly the pace of a leisurely walk when measured against the immensity of interplanetary space. These molecules, electrically neutral and invisible to magnetic fields, expand outward in all directions, creating a roughly spherical cloud of gas that grows larger with each passing hour. Into this expanding cloud flows the solar wind, its protons and electrons moving 50 times faster than the comet's sublimated gases. The resulting interactions create a complex 3-dimensional structure around the approaching visitor, a structure that exists primarily in the realm of electromagnetic fields and plasma physics rather than visible matter. Most of the comet's gas cloud remains transparent to optical telescopes, detectable only through its absorption of specific wavelengths of ultraviolet light from distant stars. The first significant modification to the solar wind occurs through a process called mass loading. As solar wind protons encounter neutral molecules from the comet, photoionization and charge exchange reactions gradually convert the comet's neutral atmosphere into plasma. This newly ionized material, unlike the original solar wind, moves at relatively slow speeds and carries the distinct isotopic and chemical signatures of the visitor's alien origin. The incorporation of this slow-moving plasma into the fast-flowing solar wind creates what plasma physicists term a pickup ion population. These newly ionized atoms and molecules become trapped by the sun's magnetic field, but their initial velocities differ dramatically from those of the ambient solar wind. The result is a local region of plasma turbulence, where magnetic field lines become tangled and particle velocities span a much wider range than normal. This turbulence represents the visitor's first significant reshaping of the solar wind's large-scale structure. Spacecraft instruments, where any positioned appropriately, would detect fluctuations in magnetic field strength and direction occurring over time scales of minutes to hours. The turbulent region extends in a teardrop shape behind the comet, with the narrow end pointing toward the sun and the broader end trailing in the anti-solar direction. The comet's nucleus itself remains too small to create a significant gravitational disturbance in the solar wind, but its growing atmosphere begins to act as a substantial obstacle to the plasma flow. The neutral gas density near the nucleus reaches levels high enough to begin absorbing and scattering solar wind particles through direct collisions. This absorption creates the first suggestion of what will eventually become a much more dramatic phenomenon: the formation of a bow shock ahead of the comet's nucleus. At these early stages of the interaction, the bow shock exists only as a subtle steepening of the solar wind's density profile. The plasma does not yet encounter a solid barrier, but rather a gradually thickening atmosphere of neutral gas and newly created ions. The solar wind begins to slow and compress as it approaches the comet, much like airflow beginning to decelerate as it approaches a mountain range still many miles distant. The magnetic field lines carried by the solar wind respond to this compression by increasing in strength and becoming more tightly packed. This magnetic compression stores energy that will later be released as the field lines reconnect and reconfigure themselves around the obstacle. The process creates a complex topology of magnetic structures. Some field lines drape around the comet's atmosphere, others become twisted into helical configurations, and still others undergo reconnection events that accelerate particles to high energies. The mystery of the visitor's internal structure deepens as telescopic observations reveal unexpected patterns in its outgassing behavior. Unlike typical solar system comets, which often develop distinct jets of material emanating from specific regions of their nuclei, the interstellar visitor appears to outgaze more uniformly across its surface. This difference might reflect a fundamental distinction in composition or structure between comets formed in our solar system and those originating around other stars. Spectroscopic analysis of the comet's emerging coma reveals isotopic ratios that confirm its extrasolar origin while raising new questions about the conditions in its parent stellar system. The ratio of deuterium to hydrogen in the comet's water vapor differs measurably from that found in Earth's oceans, suggesting formation in a stellar nebula with different temperature and radiation conditions than those that existed during our solar system's birth. The abundance of carbon monoxide relative to water vapor also marks the visitor as distinctly foreign. Solar system comets typically contain carbon monoxide in concentrations of a few percent relative to water, but the interstellar object shows ratios closer to 10 or 15%. This enhanced carbon monoxide content might reflect formation in the outer regions of its parent stellar disk, where temperatures remained low enough to condense this volatile compound efficiently. The first irony of the comet's interaction with the solar wind emerges from careful analysis of the plasma physics involved. The visitor simultaneously becomes more detectable and less substantial as it approaches the Sun. Each molecule that sublimates from its surface and ionizes in the solar wind creates a signal detectable by spectrometers millions of kilometers away, yet also represents an irreversible loss of the comet's original material. The process of observation requires the partial destruction of the object being observed. The second irony lies in the temporal scales involved. An object that has remained essentially unchanged for millions of years begins to transform dramatically over the course of weeks and months as it encounters the solar wind. The stability that preserved the comet's structure during its long journey through interstellar space becomes a liability in the dynamic environment of our solar system's inner regions. The third irony becomes apparent through modeling studies of the interaction. The visitor's modification of the solar wind creates disturbances that propagate both upstream and downstream from the comet's location. Information about the comet's presence travels upstream through the plasma at the speed of magnetoacoustic waves, preparing the solar wind for the obstacle it has not yet encountered. Meanwhile, the wake created by the comet's passage persists downstream long after the visitor has moved on, carrying chemical and isotopic traces from another stellar system into the outer reaches of our own. As the comet continues its inward journey, now approaching the asteroid belt, the solar wind density increases steadily. What began as subtle modifications to the plasma flow develop into more pronounced structures. The pickup ion population grows denser and more energetic. The magnetic field perturbations become stronger and more complex, and the first hints of Bose shock formation become detectable in the solar wind's velocity and temperature profiles. The visitor's coma, now extending across several 100,000 kilometers, begins to develop internal structure. Denser regions of gas and dust create local variations in the interaction with the solar wind, leading to the formation of multiple pressure ridges and magnetic field boundaries. The simple picture of a uniform atmosphere surrounding a solid nucleus gives way to a more complex reality of streams, eddies, and shock structures embedded within the expanding gas cloud. Behind the comet, in the anti-solar direction, the first clear evidence emerges of a plasma wake, a region where the solar wind has been deflected around the obstacle and has not yet recovered its original density and velocity. This wake region, while still subtle, represents a permanent modification to the local structure of interplanetary space. Particles of solar wind that would normally have flowed through this volume of space have been redirected around the comet's atmosphere, creating a cavity that will persist long after the visitor departs. The electromagnetic signature of this interaction begins to reach Earth as radio waves propagating at the speed of light. Radio telescopes detect the characteristic emissions of plasma turbulence and magnetic field reconnection occurring around the distant comet. These signals, encoded with information about both the visitor's composition and the structure of the solar wind at its location, represent humanity's first direct observation of plasma physics operating on the scale of an entire comet-solar wind interaction region. In the growing brightness of the inner solar system, where the Sun's disk has begun to show a measurable angular size for the first time in the comet's long journey, ancient ice and modern plasma continue their slow dance of transformation and discovery. The Bose shock begins to form in earnest as our visitor approaches the orbit of Mars, where solar wind density has increased to nearly 10 particles per cubic centimeter and the magnetic field strength has grown to several times its outer system values. This shock wave represents one of the most fundamental structures in plasma physics, a standing wave in the solar wind where the flowing plasma encounters an obstacle it cannot easily penetrate. Unlike the sonic booms created by aircraft moving through Earth's atmosphere, This bow shock exists in a medium so tenuous that individual particles might travel for hours without colliding with another particle. Instead, the shock operates through electromagnetic forces, with magnetic field lines and electric currents mediating the interaction between the solar wind and the comet's expanding atmosphere. The shock front itself measures only a few hundred kilometers thick, roughly the distance from New York to Philadelphia, yet its effects extend across millions of kilometers of space. The formation process unfolds with the inevitability of fluid dynamics operating in 4 dimensions. Solar wind protons, approaching the comet at 400 kilometers per second, encounter an increasingly dense population of neutral gas molecules and newly ionized pickup ions. The solar wind cannot simply push through this obstacle as it might through empty space. Instead, it must slow down, heat up, and deflect around the obstruction. This deceleration occurs through a process called thermalization, where the ordered motion of solar wind particles becomes randomized through electromagnetic interactions. Protons that once moved in roughly the same direction at roughly the same speed begin to scatter into a wider range of velocities and directions. The kinetic energy of their collective motion converts into thermal energy, the random motion of individual particles, raising the temperature of the plasma by factors of 3 or 4. The bow shock's 3-dimensional structure resembles a paraboloid with its focus at the comet's nucleus and its opening facing the sun. Solar wind flowing directly toward the comet encounters the shock at its strongest point. Where the deceleration is most pronounced and the heating most intense, wind flowing at oblique angles to the comet's motion encounters progressively weaker portions of the shock, until at the edges of the interaction region, the disturbance fades into the background turbulence of the normal solar wind, behind the bow shock. In the region, plasma physicists call the magnetosheath. The solar wind flows in complicated patterns around the comet's ionosphere. Here, magnetic field lines become draped around the obstacle like streamlines around a boulder in a river. Some field lines reconnect and form closed loops, trapping particles in temporary magnetic bottles. Others stretch into long, twisted configurations that channel plasma flow toward the comet's poles or around its equatorial regions. The visitor's nucleus continues its steady outgassing, now releasing several tons of material per second as solar heating intensifies. Water vapor dominates the mass loss, but carbon monoxide, methanol, hydrogen sulfide, and dozens of other molecular species contribute to the growing atmosphere. Each species responds differently to solar ultraviolet radiation, creating a complex chemistry of photodissociation products and ionization states throughout the coma. Spectroscopic observations from Earth reveal the presence of hydroxyl radicals, carbon atoms, and various molecular ions, the signatures of active photochemistry occurring in the comet's atmosphere. These observations also detect the Doppler shifts, characteristic of expanding gas, confirming that material sublimates from the nucleus and flows outward at speeds of several hundred meters per second. The mystery of the visitor's rotation period deepens as astronomers attempt to correlate brightness variations with nuclear rotation. Most solar system comets show clear periodic variations in brightness as different regions of their surfaces rotate in and out of sunlight. The interstellar visitor, however, displays more complex light curves that suggest either a tumbling rotation, an irregular shape, or non-uniform surface composition. This rotational complexity affects the structure of the bow shock and magnetosheath in subtle ways. As different regions of the nucleus outgas at different rates, the comet's atmosphere develops temporal variations in density and composition. The bow shock responds to these variations by strengthening and weakening over time scales of hours, creating ripples in the solar wind that propagate both upstream and downstream from the interaction region. The first irony of bow shock formation becomes apparent through detailed modeling. The shock wave that protects the comet's nucleus from direct solar wind bombardment also accelerates the loss of material from its surface. The heating and compression of plasma in the magnetosheath create enhanced fluxes of energetic particles that strike the comet's atmosphere with greater force than the undisturbed solar wind would provide. The second irony lies in the scale of the interaction. An object measuring only a few kilometers across creates electromagnetic disturbances that span distances comparable to the diameter of the Sun. The bow shock extends roughly 50,000 kilometers ahead of the comet's nucleus, a distance that light takes nearly 3 minutes to traverse. The third irony emerges from the temporal evolution of the system. As the comet's outgassing rate increases with closer approach to the Sun, the bow shock actually moves farther from the nucleus. The enhanced gas production creates a thicker atmosphere that pushes the shock front outward. Even though the solar wind pressure simultaneously increases downstream from the comet, the wake region continues to evolve into a more organized structure. The deflected solar wind begins to converge again behind the obstacle, but the convergence occurs gradually over distances of several million kilometers. This slow healing process creates a long, comet-shaped cavity in the solar wind, a region of reduced plasma density and altered magnetic field configuration that trails the visitor like an invisible contrail. Within this wake, magnetic field lines adopt configurations that would be impossible in the undisturbed solar wind. Some lines form closed loops that trap particles for hours or days before releasing them back into the general plasma flow. Others become twisted into helical structures that rotate slowly as they are carried downstream by the bulk motion of the solar wind. The wake also serves as a conduit for material escaping from the comet's immediate vicinity. Ions created through photoionization or charge exchange near the nucleus become entrained in the flowing plasma and carried away from the comet along magnetic field lines. These escaping ions retain the distinctive isotopic and chemical signatures of the visitor's alien origin, creating detectable traces that mark the comet's passage through interplanetary space. Radio emissions from the bow shock region begin to reach Earth with increasing intensity as the plasma interactions strengthen. These emissions, generated by energetic electrons spiraling around magnetic field lines, provide remote diagnostics of the physical conditions in the comet's immediate environment. The frequency spectrum and polarization characteristics of the radio waves reveal information about magnetic field strengths, particle densities, and temperature profiles throughout the interaction region. As the visitor approaches the orbit of Mars, now clearly visible to advanced amateur telescopes as a fuzzy star-like object, its bow shock has evolved from a subtle compression wave into a well-defined boundary between two distinct plasma regimes. Ahead of the shock lies the undisturbed solar wind, flowing steadily outward from the Sun. Behind it lies a complex region of heated, compressed, and magnetically organized plasma, a temporary modification to the structure of interplanetary space that will persist for months after the comet continues its journey toward the inner solar system. The magnetic field lines of the solar wind, invisible threads that connect the Sun to the furthest reaches of the heliosphere, begin their most dramatic transformation as they encounter our interstellar visitor approaching the orbit of Mars. These field lines, frozen into the flowing plasma by the fundamental laws of magnetohydrodynamics, cannot simply disappear when they meet an obstacle. Instead, they bend, stretch, reconnect, and drape themselves around the comet's expanding atmosphere in patterns of mathematical beauty and physical complexity. Near the comet's nucleus, where the density of neutral gas reaches its maximum, the magnetic field lines experience their most severe distortion. Solar wind protons and electrons, guided by electromagnetic forces along these field lines, find their paths increasingly disrupted by collisions with neutral atoms and molecules. Some particles undergo charge exchange reactions, becoming neutral atoms that escape the magnetic field's influence and stream away from the comet in straight lines. Others become trapped in the thickening plasma environment, contributing to the growing population of pickup ions. The process of magnetic field line draping occurs over spatial scales that dwarf the comet itself. Field lines that approach the comet from the sunward side become compressed and deflected around the obstacle, forming a pattern reminiscent of streamlines flowing around a sphere in a viscous fluid. But, unlike fluid flow, this electromagnetic draping operates in 3 dimensions, with additional complexity imposed by the field line's tendency to resist bending and their ability to reconnect when they come into close proximity. On the sunward side of the comet, magnetic field lines pile up against the growing ionosphere like cars backing up behind a traffic obstruction. This compression increases the magnetic field strength by factors of 2 to 4, storing energy that will later be released through reconnection events and particle acceleration processes. The compressed field lines also create enhanced forces that act to deflect the approaching solar wind around the comet's atmosphere. Along the flanks of the interaction region, field lines adopt curved trajectories that guide plasma flow around the comet's ionosphere. These draped field lines form the boundaries of what plasma physicists call flux tubes, long, twisted structures that channel particle motion and electromagnetic energy throughout the magnetosphere. Some flux tubes remain connected to the solar wind at both ends, allowing continued flow of particles and energy between the comet's immediate environment and the broader heliosphere. Other field lines undergo a more dramatic transformation through the process of magnetic reconnection. When field lines with opposite orientations come into close proximity, they can break and reform in new configurations that release stored magnetic energy and accelerate particles to high speeds. These reconnection events occur sporadically throughout the comet's magnetosphere, creating bright flashes of high-energy radiation and jets of accelerated plasma. The tail region behind the comet develops its own distinctive magnetic field configuration as draped field lines are carried downstream by the solar wind flow. Here, field lines from opposite flanks of the comet converge along a central sheet, a thin boundary layer where the magnetic field direction reverses and reconnection events occur with particular frequency. This current sheet extends far downstream from the comet, potentially maintaining its identity across distances measured in astronomical units. The comet's nucleus continues its steady release of neutral gas, now approaching rates of 10 tons per second as solar heating intensifies. This outgassing creates an expanding shell of material that modifies the local plasma environment on timescales ranging from minutes to hours. As neutral molecules flow outward from the nucleus, they undergo photoionization by solar ultraviolet radiation, creating new plasma with distinct velocity and temperature characteristics. The newly ionized material initially moves at the same velocity as the neutral gas from which it formed, typically a few hundred meters per second in the radial direction away from the nucleus. But once ionized, these particles become subject to electromagnetic forces and begin to gyrate around magnetic field lines with characteristic frequencies determined by their mass and charge. Protons gyrate with periods of a few seconds, while heavier ions like those from carbon monoxide or methanol have correspondingly longer gyration periods. This newly created plasma must somehow be incorporated into the ambient solar wind flow, a process that occurs through a complex sequence of plasma instabilities and wave-particle interactions. The velocity difference between the newly ionized comet material and the flowing solar wind drives various types of plasma waves, electromagnetic oscillations that propagate through the medium and scatter particles through resonant interactions. The mystery of the visitor's precise composition continues to unfold through spectroscopic observations of its growing coma. Each molecular species produces its own characteristic emission lines when excited by solar radiation or electron impact, creating a complex spectrum that encodes information about the comet's formation conditions billions of years ago. The relative abundances of different isotopes, particularly the ratios of deuterium to hydrogen, carbon-13 to carbon-12, and nitrogen-15 to nitrogen-14, provide clues about the temperature, density, and radiation environment of the stellar nebula where the comet originally formed. Some isotopic ratios match those found in the coldest regions of our own solar nebula, suggesting similar physical conditions during planetary system formation around different stars. Other ratios differ significantly, indicating exposure to stellar winds or supernova shockwaves with different compositions than those that influenced our own system's chemistry. The comet thus serves as a messenger from an alien stellar environment, carrying within its ices a record of nucleosynthesis and chemical evolution in a distant part of the galaxy. The first irony of magnetic field line draping becomes apparent through careful analysis of the field configurations. The very process that allows solar wind plasma to flow around the comet also creates pathways for energetic particles to penetrate deep into the comet's atmosphere. Reconnection events and field line instabilities accelerate particles to energies far exceeding those typical of the ambient solar wind, leading to enhanced sputtering and chemical alteration of the comet's surface materials. The second irony lies in the temporal behavior of the magnetic structures. Field lines that take hours to establish their draped configurations can be disrupted in seconds by sudden changes in the solar wind or variations in the comet's outgassing rate. The apparent stability of the magnetic field topology masks an underlying dynamism that operates on multiple timescales simultaneously. The third irony emerges from the global connectivity of the magnetic field. Disturbances created by the comet's interaction with local field lines propagate along the field lines at alpha wave speeds, potentially influencing plasma conditions at distant locations throughout the heliosphere. An object 2 kilometers across thus exerts an influence that extends across the entire solar system through the medium of magnetic field connections, as the visitor continues its approach toward the inner solar system. The magnetic field line draping becomes increasingly pronounced. Field lines that initially experienced only slight deflection now bend through large angles, storing increasing amounts of magnetic energy and creating more complex three-dimensional structures. The comet's magnetic environment evolves from a simple perturbation of the solar wind into a sophisticated magnetosphere with its own internal dynamics and characteristic phenomena. The draped field lines also begin to channel the comet's own plasma emissions in specific directions, creating the first hints of the structured ion tail that will become prominent during the comet's closest approach to the Sun. This ion tail, composed of ionized comet material accelerated along magnetic field lines, will eventually extend millions of kilometers in the anti-solar direction, a gossamer thread of alien plasma stretched across interplanetary space. The ion tail begins to emerge as our interstellar visitor crosses into the realm where Mars orbits, though this ghostly appendage remains invisible to all but the most sensitive instruments designed to detect the subtle glow of ionized gas in near vacuum. Unlike the dust tail that will later become visible to Earth-based observers, this ion tail consists purely of plasma, electrically charged atoms and molecules stripped of electrons by solar ultraviolet radiation and shaped into a narrow beam by the Sun's magnetic field. The formation of the ion tail represents a fundamental transformation in how the comet interacts with its environment. Where previously the visitor's influence on the solar wind operated primarily through the obstacle it presented to the flowing plasma, the ion tail creates a direct conduit through which the comet's material escapes into interplanetary space. Ions, created near the nucleus through photoionization, undergo acceleration along magnetic field lines, gaining speeds that can exceed 100 kilometers per second, nearly twice the velocity of the solar wind itself. This acceleration occurs through a process called magnetic pressure gradient acceleration, where ions find themselves on magnetic field lines that experience varying tension and pressure along their length. Like beads sliding down a wire under the influence of gravity, ionized atoms from the comet's atmosphere slide along field lines under the influence of magnetic forces, gaining energy as they move away from the high-pressure region near the comet's nucleus toward the lower-pressure environment of the distant solar wind. The resulting ion tail develops a complex internal structure that reflects the magnetic field topology around the comet. Near the nucleus, where field lines converge and magnetic pressure reaches its maximum, the ion tail remains narrow and dense. Further downstream, as field lines diverge and magnetic pressure decreases, the tail widens and becomes more diffuse. The overall shape resembles a narrow cone with its apex at the comet's nucleus and its base extending far into the antisolar direction. Within this plasma tail, different ionic species segregate according to their mass-to-charge ratios and their initial velocities upon ionization. Water ions, being relatively light and abundant, dominate the inner regions of the tail and achieve the highest velocities. Heavier ions from carbon monoxide, methanol, and hydrogen sulfide lag behind, creating a subtle chemical stratification within the flowing plasma. This mass separation provides astronomers with a remote method for determining the comet's composition and the relative abundances of different molecular species in its nucleus. The ion tail also serves as a natural laboratory for studying plasma physics under conditions impossible to reproduce on Earth or in spacecraft experiments. The plasma densities, magnetic field strengths, and particle energies that characterize the tail span ranges that encompass many different physical regimes, from the nearly collisionless plasmas typical of interplanetary space to the denser, more interactive plasmas found in planetary magnetospheres. Spectroscopic observations of the developing ion tail reveal emission lines characteristic of various ionization states of common elements. Singly ionized carbon monoxide produces a distinctive blue-green emission, while water ions contribute ultraviolet lines that require space-based telescopes for detection. The intensity and spatial distribution of these emission lines encode information about the density, temperature, and velocity structure of the plasma throughout the tail. The comet's nucleus continues its accelerating mass loss as solar heating intensifies with decreasing distance from the Sun. Sublimation rates now approach several tens of tons per second, creating an ever-thickening atmosphere of neutral gas around the solid nucleus. This enhanced outgassing drives stronger plasma production rates and feeds more material into the growing ion tail. Surface features on the nucleus begin to influence the outgassing pattern in ways that affect the ion tail structure. Jets of gas emanating from specific locations on the comet's surface create density enhancements in the neutral coma that translate into corresponding features in the ionized tail. These jets, likely originating from areas where subsurface ice becomes exposed to direct solar heating, inject additional complexity into the tail's morphology. The mystery of the visitor's internal structure deepens as thermal infrared observations attempt to map temperature variations across its surface. Unlike typical solar system comets, which often show distinct warm and cold regions corresponding to areas of active and inactive outgassing, the interstellar visitor displays a more uniform temperature distribution. This uniformity might indicate a more homogeneous composition throughout the nucleus, or alternatively, a surface layer that effectively redistributes absorbed solar energy. The rotation period of the nucleus, still uncertain after months of observation, appears to be either very long, perhaps several days, or the rotation axis might be oriented nearly perpendicular to the comet's orbital plane. Either configuration would reduce the amplitude of light curve variations and make period determination difficult. The rotational state affects how solar energy is distributed across the nucleus surface, influencing both the total outgassing rate and the directionality of gas jets. The first irony of ion tail formation emerges from the physics of the acceleration process. The same magnetic field lines that channel ionized comet material away from the nucleus also provide pathways for energetic solar wind particles to penetrate deeper into the comet's atmosphere. This two-way exchange means that the comet simultaneously loses its own material while gaining foreign particles from the solar wind, gradually altering its surface composition and isotopic ratios. The second irony lies in the visibility characteristics of the ion tail. This most dramatic manifestation of the comet's interaction with the solar wind remains essentially invisible to human eyes and conventional optical telescopes. The plasma densities, while enormous compared to typical interplanetary values, remain far too low to scatter significant amounts of visible light. The tail can be detected only through its own faint emission lines or through its absorption of background ultraviolet radiation from distant stars. The third irony becomes apparent through comparison with solar system comets. The interstellar visitor's ion tail, formed from material that originated around another star billions of years ago, now glows with emission lines that encode the same physical processes occurring in all plasma tails throughout the solar system. The alien chemistry produces familiar spectroscopic signatures, demonstrating the universality of atomic physics across different stellar environments. As the comet continues inward, approaching the orbit of Earth, the ion tail extends across increasingly vast distances behind the nucleus. Magnetic field lines draped around the comet now stretch millions of kilometers in the anti-solar direction, creating a plasma structure that dwarfs anything produced by the solid nucleus itself. The tail's faint glow, detectable only by specialized instruments, marks the path of the visitor's passage through interplanetary space with a trail of ionized alien matter. The solar wind flowing around the comet's magnetosphere carries some of this ionized material away from the immediate tail region, distributing it more broadly throughout the heliosphere. Ions that escape from the main tail structure become incorporated into the general solar wind flow, adding their distinctive isotopic signatures to the plasma that eventually reaches the heliopause and influences the boundary between our solar system and the interstellar medium. The ion tail thus serves as both a conduit for material loss from the comet and a mechanism for injecting alien matter into our solar system's plasma environment. This injection occurs on scales too small to affect planetary atmospheres or space weather phenomena, but large enough to be detectable by sensitive mass spectrometers on spacecraft positioned appropriately to sample the modified solar wind. In the growing brilliance of the inner solar system, where the sun now appears as a clearly defined disk rather than a point source, the visitor's plasma tail streams away like a banner of ionized matter, marking the comet's passage through our star's domain with glowing testimony to the electromagnetic forces that shape the space between worlds. A cavity begins to form in the solar wind, an absence more significant than any presence. A void carved by the passage of our interstellar visitor through the flowing plasma of the sun's extended atmosphere. This cavity emerges not as a simple hollow space, but as a complex, three-dimensional region where particle densities drop below normal values. Magnetic field lines adopt unusual configurations, and the bulk flow velocity of the solar wind deviates from its typical radial pattern. The formation of this cavity occurs through multiple physical processes operating simultaneously across different spatial and temporal scales. Direct absorption of solar wind particles by the comet's expanding atmosphere removes protons and electrons from the ambient plasma, creating local depletions in particle density. Mass loading through ionization of neutral comet material adds slow-moving ions to the plasma flow, reducing the bulk velocity and altering the momentum balance. Magnetic field line draping redirects plasma flow around the comet's ionosphere, creating wake regions where normal solar wind densities take time to recover. The cavity extends far beyond the immediate vicinity of the comet's nucleus, reaching dimensions comparable to the distance between Earth and its moon. At its widest point, near the comet's nucleus, the particle density drops to perhaps half its normal value, still an excellent vacuum by terrestrial standards, but a substantial deviation in the context of interplanetary space. The cavity tapers gradually in the antisolar direction, where deflected solar wind slowly converges to fill the wake region left by the comet's passage. Within this evacuated region, the remaining plasma exhibits properties that distinguish it clearly from the undisturbed solar wind. Temperature measurements would show elevated values, reflecting the heating that occurs as solar wind particles undergo thermalization and energy exchange with newly ionized comet material. Magnetic field measurements would reveal enhanced field strengths and complex orientations, as field lines become compressed and tangled by their interaction with the expanding comet atmosphere. The cavity also serves as a reservoir for comet-derived material that cannot escape through the ion tail. Heavy molecular ions, created through photoionization of complex organic compounds in the comet's coma, often lack sufficient energy to overcome the magnetic pressure gradients that drive tail formation. These ions remain trapped in the cavity region, creating a distinct population of plasma with isotopic and chemical signatures that mark its alien origin. Plasma waves propagate throughout the cavity region, generated by various instabilities associated with the comet's solar wind interaction. Ion cyclotron waves, created by the gyrational motion of newly ionized particles, modify the local magnetic field structure and scatter particles through resonant interactions. Lower frequency magnetosonic waves carry energy and momentum throughout the interaction region, coupling processes occurring near the comet's nucleus with phenomena occurring far downstream in the wake. The three-dimensional structure of the cavity reflects the complex geometry of the magnetic field lines draped around the comet's ionosphere, near the subsolar point, where the solar wind flow directly impacts the comet's atmosphere. The cavity reaches its maximum depth and smallest lateral extent along the flanks of the interaction region. The cavity becomes shallower but extends over larger areas, as deflected plasma flow creates broad regions of reduced density. The mystery of the cavity's detailed structure requires sophisticated computer simulations to unravel, as the governing equations of magnetohydrodynamics become highly nonlinear in regions where plasma densities and magnetic field strengths vary significantly over short distances. Current computational models can capture the large-scale features of the interaction, but detailed predictions of plasma properties at specific locations within the cavity remain challenging. Observational studies of the cavity face the fundamental difficulty that most plasma diagnostic techniques require either direct in situ measurements by spacecraft instruments or remote sensing of electromagnetic emissions. The cavity's location, following the comet as it moves through the solar system, makes spacecraft encounters unlikely. While its plasma densities remain too low for strong electromagnetic emission, most information about the cavity's properties must therefore be inferred from observations of the comet itself and theoretical modeling of plasma physics processes. The temporal evolution of the cavity occurs on multiple timescales that reflect different aspects of the physical processes involved. Short-term variations, occurring over minutes to hours, reflect changes in the comet's outgassing rate due to rotational modulation of solar heating or the activation of new gas jets from the nucleus surface. Intermediate-term changes, spanning days to weeks, reflect the comet's changing distance from the Sun and the corresponding evolution of solar wind properties along its orbital path. Long-term evolution of the cavity, extending over months, reflects the fundamental progression of the comet's interaction with the solar wind as outgassing rates increase toward perihelion passage and then decline during the outbound journey. The cavity reaches its maximum development around the time of the comet's closest approach to the Sun, when outgassing rates and solar wind interaction effects both achieve their peak intensity. The first irony of cavity formation lies in its ephemeral nature, a structure that spans millions of cubic kilometers of space and influences plasma flow patterns across an even larger volume exists only as long as the comet remains in the vicinity. Once the visitor continues its journey toward the outer solar system, the cavity begins to collapse as normal solar wind flow gradually refills the evacuated region. The second irony emerges from the relationship between the cavity's size and the comet's intrinsic dimensions. An object measuring perhaps 2 kilometers across creates a plasma disturbance that extends across distances comparable to planetary orbits. The cavity represents a temporary modification to the large-scale structure of the heliosphere, demonstrating how relatively small objects can influence their environment across vast scales when the appropriate physical processes are involved. The third irony becomes apparent through consideration of the cavity's composition. A region of space depleted in solar wind plasma becomes enriched in material from another stellar system. The cavity serves as a temporary repository for alien chemistry within our solar system's plasma environment, creating a localized region where the isotopic and molecular signatures of interstellar matter dominate over the solar wind's terrestrial composition. As the comet approaches the orbit of Earth, the cavity reaches substantial development, with plasma density depletions extending across millions of kilometers behind the nucleus. Solar wind streamlines, normally flowing radially outward from the Sun with only minor deflections, now curve significantly around the obstacle presented by the comet's interaction region. The resulting flow pattern resembles that of a river dividing around an island, with convergent flow patterns downstream where the deflected streams begin to merge again. Within the cavity, energetic particle populations develop through acceleration processes associated with magnetic field line reconnection and plasma wave interactions. These particles, while far too sparse to pose hazards to spacecraft, create detectable signatures in radio wave emissions and high-energy radiation that can be observed from Earth-based facilities. The cavity also influences the propagation of solar energetic particles, high-energy protons and electrons accelerated by solar flares and coronal mass ejections. These particles, normally guided by magnetic field lines throughout the heliosphere, encounter altered field configurations within the cavity region that can focus, defocus, or scatter them in ways that differ from their behavior in the undisturbed solar wind. The visitor continues to carve its temporary channel through the solar wind, leaving behind a wake region that will persist for months after the comet itself has departed the inner solar system. This wake serves as a fossil record of the interaction, preserving information about both the comet's properties and the state of the solar wind during the encounter. Dust grains begin their own migration away from the comet's nucleus, following trajectories that differ fundamentally from those of the ionized gas that forms the plasma tail. These microscopic particles, ranging in size from nanometers to millimeters, carry within their solid structure the most pristine samples of material from the comet's birth around another star. Unlike the gas molecules that undergo chemical transformation and ionization in the solar wind, dust grains preserve their original composition and crystalline structure as they drift slowly away from the nucleus under the gentle but persistent influence of solar radiation pressure. The liberation of dust from the comet's surface occurs through multiple mechanisms that operate simultaneously as solar heating intensifies. Sublimation of water ice and other volatile compounds creates gas pressure that lifts dust particles from the nucleus surface. Much like steam escaping from a boiling kettle carries along droplets of liquid water, thermal cycling between the comet's day and night sides creates mechanical stresses that fracture surface materials, releasing fragments ranging from fine powder to pebble-sized chunks. Direct solar heating of dark dust particles embedded in surface ice creates localized hotspots that enhance sublimation rates in their immediate vicinity, undermining the structural support that holds larger particles in place. These thermal effects operate most efficiently on the sunward-facing hemisphere of the nucleus, but the comet's rotation ensures that all surface regions eventually experience solar heating and contribute to dust production. The dust grains, once liberated from the nucleus surface, begin their independent journey through interplanetary space under the influence of forces that depend critically on particle size and composition. Solar radiation pressure acts most effectively on the smallest particles, accelerating them to velocities that can exceed those of the gas molecules from which they separated. Larger particles experience relatively weaker radiation pressure effects and maintain velocities closer to their initial ejection speeds from the nucleus surface. This size-dependent acceleration creates a natural sorting mechanism that segregates dust particles according to their dimensions as they move away from the comet, the smallest particles, with dimensions measured in nanometers, achieve the highest velocities and form the leading edge of the dust cloud. Intermediate-sized particles, measuring micrometers across, occupy the middle regions of the expanding dust envelope. The largest particles, those approaching millimeter dimensions, lag behind and remain closest to the nucleus throughout the comet's passage through the inner solar system. The trajectories, followed by dust particles, also depend on their initial ejection direction from the nucleus surface. Particles expelled in the antisolar direction receive additional acceleration from radiation pressure that acts in the same direction as their initial motion. Particles ejected toward the Sun or perpendicular to the Sun-comet line experience more complex acceleration patterns that can curve their trajectories significantly over time. The resulting dust cloud develops a complex three-dimensional structure that reflects both the physics of particle ejection and the subsequent influence of solar radiation. Near the nucleus, where ejection velocities dominate over radiation pressure effects, the dust distribution remains roughly spherical. Further from the nucleus, radiation pressure increasingly shapes the particle trajectories, creating a fan-shaped distribution that opens in the anti-solar direction. Compositional analysis of the dust grains, accomplished through spectroscopic observation of their thermal emission and scattered sunlight, reveals the heterogeneous nature of the comet's solid materials. Silicate minerals, likely formed in the condensation zones of the original stellar nebula, contribute infrared emission features characteristic of olivine, pyroxene, and other rock-forming minerals. Carbonaceous compounds, possibly including complex organic molecules formed through radiation processing in interstellar space, produce broader absorption features that indicate a rich chemistry of carbon-bearing materials. The dust grains also preserve isotopic signatures that provide clues about the nuclear processes occurring in the comet's parent star and the surrounding stellar environment. The ratio of magnesium-24 to magnesium-26, for example, reflects the abundance of aluminum-26 in the stellar nebula at the time of grain formation. This short-lived radioactive isotope, produced in massive stars and dispersed through supernova explosions, serves as a chronometer for dating the formation of solid materials in stellar systems. Crystalline structure analysis of the dust grains, inferred from polarization measurements of scattered sunlight, suggests formation under conditions of slow cooling and low shock pressure. This finding implies that the comet's solid materials condensed gradually from the gaseous phase in the outer regions of its parent stellar disk, rather than forming through high-temperature processes closer to the central star. The preservation of these delicate crystalline structures also indicates that the comet has experienced minimal heating and mechanical disturbance during its long journey through interstellar space. The mystery of the dust grain size distribution deepens as observational data reveal patterns that differ from those typically observed in solar system comets. The interstellar visitor produces fewer large particles and more small particles than would be expected based on models of comet nucleus structure and sublimation processes. This difference might reflect fundamental distinctions in formation processes between interstellar comets and those native to our solar system. The temporal evolution of dust production shows complex variations that correlate with the comet's rotation period and its changing distance from the Sun. Periodic brightness variations, with amplitudes of several percent, indicate that different regions of the nucleus surface contribute varying amounts of dust to the expanding cloud. These variations provide astronomers with a remote method for mapping the distribution of volatile and refractory materials across the nucleus surface. The first irony of dust grain dynamics becomes apparent through detailed trajectory analysis. Particles that require millions of years to travel between star systems can be accelerated to high velocities over distances of only a few million kilometers by the gentle pressure of solar radiation. The same sunlight that gradually warmed the comet during its approach provides the energy needed to disperse its solid materials throughout the inner solar system. The second irony lies in the preservation of information. Dust grains that survive unchanged for billions of years in the harsh environment of interstellar space begin to undergo rapid alteration within months of entering the inner solar system. Solar heating, charged particle bombardment, and micrometeorite impacts gradually modify the grain's surfaces and potentially alter their internal structure, erasing some of the information they carried about conditions in their parent stellar system. The third irony emerges from the scale of the dust cloud. Microscopic particles, individually invisible to the most powerful telescopes, collectively create a structure that spans millions of kilometers and becomes detectable from Earth through the sunlight they scatter. The dust cloud eventually grows larger than the orbit of Mars, making it one of the most extended objects in the solar system during the comet's passage through the inner regions. As the visitor continues its approach toward perihelion, dust production rates accelerate in response to increasing solar heating. The expanding dust cloud begins to develop the curved tail structure that will eventually become visible to Earth-based observers, creating a ghostly appendage that traces the comet's orbital path through space. This dust tail, composed of alien materials from another stellar system, will persist long after the comet's departure, gradually dispersing throughout the inner solar system and adding its microscopic contribution to the zodiacal dust cloud that surrounds our Sun. The dust grains thus serve as both messengers from the distant past and tracers of present-day dynamical processes, carrying information across interstellar distances while simultaneously creating new structures within our own solar system's architecture. The heliospheric current sheet, a vast, undulating boundary that separates regions of opposite magnetic polarity throughout the solar system, encounters our interstellar visitor as it crosses Earth's orbital distance from the Sun. This encounter represents one of the most subtle, yet far-reaching consequences of the comet's passage through our stellar domain, as the visitor's magnetic field disruptions propagate along field lines that extend from the Sun's polar regions to the heliopause itself. The current sheet itself exists as one of the largest coherent structures in the solar system, a warped surface that extends from the Sun's equatorial regions outward to distances beyond the orbit of Pluto. Its undulating shape reflects the complex geometry of the Sun's rotating magnetic field, which creates a pattern resembling the pleated skirt of a spinning dancer. The sheet thickness measures only a few hundred kilometers, thinner than Earth's atmosphere when scaled to planetary dimensions. Yet it influences plasma flow patterns and energetic particle propagation throughout the entire heliosphere. When the comet's bow, shock, and magnetospheric disturbances encounter this current sheet, the interaction creates localized modifications to the magnetic field topology that can propagate far beyond the immediate vicinity of the visitor. Magnetic field lines that normally maintain their connection to specific solar surface regions become temporarily disconnected and reconnected in new configurations, creating pathways for energy and particle transport that would not exist in the undisturbed heliosphere. The physics of this interaction operates through magnetic reconnection events that occur where the comet's draped field lines come into contact with the current sheet boundary. These reconnection processes release stored magnetic energy and accelerate particles to energies significantly higher than those typical of the ambient solar wind. The accelerated particles then propagate along the reconnected field lines, carrying information about the comet's presence to distant regions of the heliosphere. Plasma waves generated by the comet current sheet interaction travel at speeds comparable to the solar wind velocity, taking days to weeks to reach the outer boundaries of the solar system. These waves carry distinctive signatures that encode information about both the comet's properties and the state of the interplanetary magnetic field at the time of the encounter. Advanced space-based instruments positioned throughout the heliosphere can potentially detect these signatures and use them to study both comet physics and large-scale heliospheric structure. The comet's nucleus continues its accelerating sublimation as solar heating reaches unprecedented levels in its long history. Mass loss rates now exceed 100 tons per second, creating an atmosphere around the nucleus that rivals some planetary atmospheres in extent, though remaining far more tenuous than even Mars's thin envelope of carbon dioxide. This enhanced outgassing drives more vigorous plasma production and strengthens the electromagnetic disturbances that affect the current sheet interaction. The coma surrounding the nucleus has expanded to dimensions larger than Jupiter, though its extremely low density makes it essentially transparent to visible light. Within this vast atmosphere, complex chemical reactions occur as solar ultraviolet radiation breaks apart molecules and creates reactive fragments that can recombine in unexpected ways. Some of these reactions produce species that do not exist naturally in Earth's environment, creating a temporary chemical laboratory for studying molecular processes under conditions impossible to duplicate in terrestrial facilities. Spectroscopic observations reveal the presence of exotic molecular ions and radicals that exist only in the rarefied environment of the comet's coma. These species provide information about the original composition of materials formed around other stars, while also demonstrating the universal nature of chemical processes throughout the galaxy. The same quantum mechanical principles that govern molecular behavior in Earth's atmosphere operate identically in the alien chemistry of the interstellar visitor's atmosphere. The mystery of the current sheet's response to comet interactions deepens as theoretical models struggle to predict the detailed consequences of such encounters. The magnetic field topology of the heliospheric current sheet involves complex three-dimensional structures that change continuously as the sheet rotates with the sun and responds to variations in solar activity. Adding the perturbations created by comet passage creates a computational challenge that taxes even the most powerful supercomputers. Observational confirmation of current sheet modifications requires coordinated measurements from multiple spacecraft positioned at different locations throughout the heliosphere. Such observations remain rare, as most space missions focus on specific planetary targets rather than the large-scale structure of interplanetary space. The few available measurements suggest that comet current sheet interactions do produce detectable effects, but the limited data make it difficult to develop comprehensive understanding of the phenomenon. The temporal evolution of the interaction occurs over multiple characteristic timescales that reflect different physical processes. The initial encounter between the comet's magnetic disturbances and the current sheet occurs over periods of hours to days. As the visitor's magnetosphere intersects the sheet boundary, the propagation of disturbances along current sheet field lines takes additional days to weeks, as modified plasma conditions spread throughout the heliospheric structure. The first irony of the current sheet interaction emerges from its global consequences. A localized disturbance created by an object only a few kilometers across can influence magnetic field configurations and particle populations throughout the entire solar system. The comet serves as a small perturbation that reveals the interconnected nature of heliospheric dynamics, demonstrating how local physics processes can have far-reaching consequences in the solar wind environment. The second irony lies in the detection challenges. The most significant large-scale consequence of the comet's passage through our solar system also represents one of the most difficult effects to observe and quantify. While the comet itself becomes increasingly visible to Earth-based telescopes, its influence on the heliospheric current sheet remains largely invisible, detectable only through subtle changes in magnetic field measurements and energetic particle populations recorded by distant spacecraft. The third irony becomes apparent through comparison with typical solar system phenomena. The interaction between an interstellar visitor and our Sun's magnetic field creates disturbances that propagate farther and persist longer than many solar flares and coronal mass ejections. The comet's gentle but persistent influence on heliospheric structure contrasts with the dramatic but transient effects of explosive solar activity. As the visitor continues toward its closest approach to the Sun, its interaction with the heliospheric current sheet intensifies. The growing strength of the comet's plasma environment creates larger magnetic field perturbations that affect increasingly extensive regions of the current sheet. These disturbances will continue to propagate outward long after the comet has passed perihelion and begun its journey back toward interstellar space. The current sheet interaction also influences the comet's own plasma environment, as the encounter with this large-scale magnetic structure modifies the field line topology around the nucleus. Some field lines become connected to the current sheet for extended periods, creating enhanced pathways for particle escape and energy transport away from the comet's immediate vicinity. The heliospheric current sheet, normally invisible and detectable only through its effects on charged particle motion, thus becomes temporarily modified by its encounter with our ancient visitor, creating a subtle but persistent signature of interstellar matter's passage through the electromagnetic architecture of our solar system. Perihelion approaches with the mathematical certainty of orbital mechanics, marking the moment when our interstellar visitor will reach its closest approach to the Sun and experience the maximum intensity of solar heating in its billion-year journey through space. At this point in its trajectory, roughly 90 million kilometers from the Sun's surface, the comet will receive solar energy at levels more than 4,000 times greater than it experienced during its long drift through the outer solar system. The effects of this enhanced heating begin to manifest weeks before the actual perihelion passage, as the inverse square law of radiation ensures that solar energy input increases rapidly with decreasing distance. Surface temperatures on the nucleus, previously hovering near the temperature of liquid nitrogen, begin to rise toward values that approach the freezing point of water on the sunward-facing hemisphere. This temperature increase drives sublimation rates to their maximum levels, creating mass loss rates that peak at several hundred tons per second. The comet's nucleus, now releasing material at rates that would completely exhaust a typical asteroid in a matter of months, creates an atmosphere around itself that extends across millions of kilometers of space. This coma, while remaining far more tenuous than any planetary atmosphere, nonetheless contains enough neutral gas to significantly alter the local plasma environment and create the most dramatic manifestations of the comet-solar wind interaction. The bow shock ahead of the comet reaches its maximum development during this period, extending nearly 100,000 kilometers sunward from the nucleus. This shock front, now clearly defined and readily detectable by plasma instruments, decelerates and heats the solar wind by factors that make the shocked plasma comparable in temperature to the Sun's corona, though at densities millions of times lower. Behind the bow shock, in the magnetosheath region, plasma temperatures exceed 1 million degrees while particle densities reach levels 10 times higher than those found in the undisturbed solar wind. These extreme conditions, existing in a volume of space larger than Jupiter, create a natural laboratory for studying plasma physics under conditions that cannot be achieved in any terrestrial experiment. The ion tail reaches its maximum extension during perihelion passage, stretching across distances that span significant fractions of an astronomical unit. This ghostly appendage composed of ionized comet material accelerated to high speeds by magnetic field line tension, creates a structure that rivals the largest planetary magnetospheres in spatial extent. Within the tail, plasma densities remain extremely low by terrestrial standards, yet the total amount of ionized material flowing away from the comet approaches several tons per second. The dust tail also achieves its greatest development around perihelion, as enhanced sublimation rates lift increasing quantities of solid material from the nucleus surface. Unlike the ion tail, which responds almost instantaneously to changes in solar wind conditions, the dust tail evolves more slowly as particles of different sizes separate according to their responses to solar radiation pressure. The largest dust particles, those approaching millimeter dimensions, remain relatively close to the nucleus and follow trajectories that closely resemble the comet's orbital path. Smaller particles experience stronger acceleration from radiation pressure and begin to curve away from the comet's motion, creating the characteristic swept-back appearance of comet tails as seen from Earth. The smallest particles, those measuring nanometers across, achieve velocities that can exceed the orbital velocity of the comet itself, allowing them to escape the immediate vicinity of the nucleus and contribute to the zodiacal dust cloud that permeates the inner solar system. These microscopic fragments of interstellar matter will eventually be swept up by planetary atmospheres or removed from the solar system by radiation pressure. But during their transit, they serve as traces of the comet's passage through our stellar domain. The mystery of the comet's internal structure begins to reveal itself through detailed observations of the outgassing behavior during maximum activity. Unlike solar system comets, which often display highly asymmetric outgassing patterns due to variations in surface composition and subsurface structure, the interstellar visitor maintains a relatively uniform sublimation rate across its surface. This uniformity suggests either a homogeneous composition throughout the nucleus or an efficient mechanism for distributing absorbed solar energy. Thermal infrared observations during perihelion passage reveal surface temperatures that vary by only a few degrees across different regions of the nucleus. Despite the fact that solar heating should create significant temperature gradients between the sunward and anti-sunward hemispheres, this temperature uniformity indicates either rapid thermal conduction within the nucleus or substantial subsurface heat sources created by the sublimation of volatile materials. The rotation period of the nucleus, finally determined through careful photometric monitoring during maximum brightness, proves to be approximately 18 hours, longer than typical for solar system comets, but consistent with the visitor's overall unusual characteristics. This relatively slow rotation contributes to the temperature uniformity by ensuring that all surface regions spend substantial time in direct sunlight during each rotation cycle. The first irony of maximum solar heating emerges from the timing of peak activity. The comet achieves its most dramatic interactions with the solar wind environment precisely when it begins its irreversible journey back toward interstellar space. The peak of activity marks not a beginning, but a turning point, after which all manifestations of the comet's solar-wind interaction will gradually diminish. The second irony lies in the relationship between visibility and substance. The comet becomes most apparent to Earth-based observers at exactly the moment when it loses material at its highest rate. The enhanced brightness that makes the visitor detectable to amateur astronomers represents the destruction of materials that survived billions of years of interstellar travel. The third irony becomes apparent through consideration of the energy balance. The same solar heating that drives maximum outgassing and creates the most spectacular plasma phenomena also begins the process of thermal alteration that will modify the surface composition and potentially erase some of the isotopic and chemical signatures that mark the comet's interstellar origin. The plasma cavity carved by the comet's passage reaches its maximum dimensions during perihelion, creating a void in the solar wind that extends across distances comparable to the diameter of Mercury's orbit. Within this cavity, plasma densities drop to values lower than those found in the most perfect laboratory vacuums. Yet the region remains filled with complex electromagnetic phenomena and energetic particle populations. The wake region behind the comet develops increasingly complex structure as the enhanced plasma production drives stronger instabilities and more vigorous magnetic reconnection events. Magnetic field lines threading the wake adopt configurations that would be unstable in most other astrophysical environments, persisting only because of the continuous energy input provided by the ongoing comet-solar-wind interaction. As perihelion passage concludes and the comet begins its outbound journey, the peak intensity of all interaction phenomena marks a transition point in the visitor's relationship with our solar system. The maximum effects achieved during closest approach to the Sun will gradually diminish over the coming months, but the modifications to heliospheric structure and the dispersed trails of interstellar material will persist long after the comet itself has departed for the outer darkness. The wake persists with a stubbornness that defies intuition, stretching behind our departing visitor like an invisible scar carved through the fabric of interplanetary space. Long after the comet has passed perihelion and begun its journey toward the outer solar system, the cavity it created in the solar wind maintains its identity as a distinct region of altered plasma properties and modified magnetic field configurations. This persistence occurs because the solar wind, despite its supersonic velocity, requires substantial time to refill the evacuated region left by the comet's passage. The wake extends millions of kilometers in the anti-solar direction, creating a volume of space where plasma densities remain below normal values and magnetic field lines retain the twisted, reconnected configurations imposed by their interaction with the visitor's magnetosphere. The healing process operates through multiple physical mechanisms that act on different spatial and temporal scales. Solar wind plasma flowing around the edges of the wake gradually converges toward the central axis, but this convergence must overcome the magnetic pressure of the enhanced field lines threading the wake region. The result is a slow, complex process that may require months or even years for complete restoration of undisturbed solar wind conditions. Within the wake, residual populations of pickup ions continue to modify the local plasma environment long after their parent comet has moved beyond the inner solar system. These ions, created through ionization of neutral comet material during the peak interaction period, remain trapped by magnetic field lines and contribute to enhanced plasma wave activity throughout the wake region. The three-dimensional structure of the persistent wake reflects the complex history of the comet-solar-wind interaction near the wake's central axis, where the comet's influence was strongest. Plasma densities remain most severely depleted and magnetic field perturbations retain their greatest amplitude. Toward the edges of the wake, conditions gradually transition toward normal solar wind values, creating boundary layers where plasma instabilities and wave phenomena remain active. Magnetic reconnection events continue to occur sporadically throughout the wake region, as field lines with different orientations and histories come into contact and rearrange themselves into lower energy configurations. These reconnection events accelerate particles to high energies and generate electromagnetic emissions detectable by radio telescopes throughout the inner solar system. The wake also serves as a conduit for the continued escape of material from the comet's trailing plasma environment. Ion populations created near the nucleus during perihelion passage require weeks or months to propagate along field lines to the distant boundaries of the wake region. This delayed material transport means that the chemical and isotopic signatures of the interstellar visitor continue to appear in plasma measurements long after direct outgassing from the nucleus has diminished. Energetic particle populations within the wake exhibit complex temporal variations that reflect the history of acceleration processes occurring throughout the interaction region. Particles accelerated during different phases of the comet's approach and departure carry information about the evolving conditions in the plasma environment, creating a kind of fossil record of the interaction encoded in particle energy and arrival time distributions. The mystery of wake longevity remains an active area of research in space plasma physics, as theoretical models struggle to predict accurately the timescales required for complete dissipation of comet-induced disturbances. Computer simulations suggest that some aspects of the wake structure may persist for years, while others disappear within weeks of the comet's passage. Observational studies of wake persistence face the fundamental challenge that most space-based instruments move through the solar system along trajectories that do not intersect the wake regions of departing comets. The few available measurements come from spacecraft that happen to encounter wake regions by chance, providing limited statistical samples for understanding the general properties of these structures. The wake's influence on solar energetic particle propagation creates one of its most far-reaching effects on heliospheric physics. High-energy protons and electrons accelerated by solar flares encounter altered magnetic field configurations within the wake region that can focus, defocus, or scatter the particles in ways that differ significantly from their behavior in the undisturbed solar wind. These particle scattering effects can influence space weather phenomena throughout the inner solar system, as energetic particles that would normally follow predictable paths along magnetic field lines encounter unexpected deflections within wake regions. The resulting modifications to particle arrival times and intensity profiles at various locations create subtle but measurable changes in radiation environments around planets and spacecraft. The first irony of wake persistence emerges from its relationship to the comet's physical presence. The most long-lasting consequence of the visitor's passage through our solar system consists entirely of empty space, regions where normal solar wind has been removed rather than where foreign material has been added. The comet's absence creates a more durable signature than its presence. The second irony lies in the detection challenges. The wake represents the largest single structure created by the comet's interaction with our solar system. Yet, it remains essentially invisible to conventional astronomical observations. While the comet itself appears as a point of light visible to telescopes, the wake that dwarfs it in spatial extent can be detected only through sophisticated plasma physics measurements. The third irony becomes apparent through consideration of information content. The wake preserves a more detailed record of the comet's solar wind interaction than any other observational signature. The spatial distribution of plasma properties throughout the wake encodes information about magnetic field configurations, particle acceleration processes, and chemical composition that cannot be obtained from direct observations of the comet itself. As the comet continues its outbound journey beyond the orbit of Mars, the wake structure begins its gradual evolution toward eventual dissipation. The boundaries become less distinct as diffusion processes smooth out the sharp gradients in plasma properties. Internal structures within the wake become less organized as magnetic field lines undergo reconnection and relaxation toward minimum energy states. Yet even as the wake slowly dissolves, it continues to influence plasma processes throughout its volume. Turbulence levels remain elevated compared to the undisturbed solar wind, creating enhanced rates of particle scattering and energy dissipation. These effects contribute to the overall heating and acceleration of the solar wind as it flows outward through the heliosphere. The wake also serves as a preferred site for the generation of plasma waves that can propagate far beyond the immediate interaction region. Low-frequency waves generated by instabilities within the wake can travel along magnetic field lines to distant parts of the solar system, carrying signatures of the comet encountered to locations that never experienced direct interaction with the visitor itself. Dust particles trapped within the wake region follow complex trajectories as they respond to electromagnetic forces and radiation pressure effects modified by the altered plasma environment. Some particles become temporarily confined within magnetic field structures, while others experience enhanced acceleration that ejects them from the wake region at high velocities. The persistent wake thus serves as both a fossil record of the comet's passage and an active agent for continued modification of heliospheric structure and dynamics, demonstrating how transient events can create long-lasting changes in the solar wind environment. Word count 1152. Awaiting continue section 12. Earth's magnetosphere, that vast invisible shield that protects our planet from the solar wind's continuous bombardment, encounters the modified plasma flowing in the wake of our departed interstellar visitor as our world's orbital motion carries it through regions of space altered by the comet's passage. This encounter occurs months after the visitor itself has moved beyond the inner solar system, demonstrating the persistent nature of the disturbances carved into the solar wind by objects that briefly traverse our stellar domain. The interaction unfolds as Earth's bow shock, the standing wave that forms where our planet's magnetic field deflects the approaching solar wind, encounters plasma with properties that differ subtly but measurably from the undisturbed solar wind. Particle densities in the comet's wake remain several percent below normal values, while magnetic field strengths show corresponding enhancements due to the conservation of magnetic flux in the partially evacuated region. These modifications to solar wind properties propagate through Earth's magnetospheric system in ways that create detectable but subtle changes throughout our planet's electromagnetic environment. The slightly reduced plasma density leads to a modest expansion of the magnetosphere, as the balance between solar wind pressure and terrestrial magnetic pressure shifts in favor of the magnetic field. This expansion moves the magnetopore's boundary outward by perhaps 1,000 kilometers, a small change in absolute terms, but significant in the context of a magnetospheric dynamics. Within the magnetosphere, populations of trapped charged particles respond to the altered solar wind conditions through changes in their distribution functions and energy spectra. The Van Allen radiation belts, those toroidal regions where high-energy protons and electrons remain confined by Earth's magnetic field, show variations in particle intensities that reflect the modified boundary conditions imposed by the comet-influenced solar wind. Auroral activity displays corresponding modifications, as the processes that accelerate particles into Earth's upper atmosphere depend sensitively on the coupling between the solar wind and terrestrial magnetosphere. The efficiency of energy transfer from the solar wind to the magnetosphere changes when the impinging plasma carries the signatures of comet interaction, leading to aurora with slightly different brightness, color distributions, and spatial patterns. The ionosphere, Earth's uppermost atmospheric layer where solar radiation creates a tenuous plasma of ionized atmospheric gases, responds to these magnetospheric changes through alterations in the electric fields and currents that couple the ionosphere to the magnetosphere above. Radio wave propagation characteristics change minutely as ionospheric plasma densities adjust to the modified electromagnetic environment. Ground-based magnetometers record the passage of the comet's wake as subtle variations in Earth's magnetic field that differ from the typical patterns associated with normal solar wind fluctuations. These variations, while requiring sophisticated analysis techniques to identify clearly, provide terrestrial observers with a method for remotely sensing the properties of plasma structures that formed around the comet during its earlier passage through the inner solar system. The comet's wake also carries within its volume trace populations of pickup ions that originated from the sublimation and ionization of the visitor's nucleus during perihelion passage. These ions, bearing the isotopic and chemical signatures of materials formed around another star, become incorporated into Earth's magnetosphere when our planet's magnetic field captures particles from the surrounding solar wind. The concentrations of these interstellar ions remain far too low to influence terrestrial atmospheric chemistry or biological processes, but they provide scientists with the opportunity to study alien matter using Earth-based laboratory facilities. Mass spectrometers aboard research satellites can potentially identify individual ions of interstellar origin and determine their composition with precision impossible to achieve through remote astronomical observations. The mystery of how efficiently Earth's magnetosphere can capture and retain particles from comet wakes remains an active area of research in magnetospheric physics. Theoretical models suggest that the capture process depends critically on the particles' initial velocities and the magnetic field configurations they encounter, both of which vary significantly throughout the wake region. Some comet-derived ions may become permanently trapped in Earth's radiation belts, where they could remain for years before atmospheric drag or other loss processes remove them from the magnetosphere. Other ions may simply pass through the magnetospheric system without significant interaction, continuing their journey toward the outer heliosphere as temporary components of the solar wind. The temporal evolution of Earth's encounter with the comet wake occurs over timescales ranging from hours to weeks, depending on the spatial extent of the wake and Earth's velocity relative to the modified solar wind flow. The initial contact creates transient effects that last for hours as the planet's magnetosphere adjusts to the altered boundary conditions. More persistent effects may continue for days or weeks as populations of trapped particles slowly respond to the changed electromagnetic environment. The first irony of the magnetospheric encounter becomes apparent through consideration of the spatial scales involved. Earth's magnetosphere, one of the largest structures associated with our planet, becomes temporarily modified by disturbances created by an object thousands of times smaller than Earth itself. The comet's influence propagates through the solar wind and ultimately affects plasma processes in Earth's immediate vicinity. The second irony lies in the timing of the interaction. Earth samples the comet's influence on the solar wind long after any possibility of direct interaction with the visitor itself. The modified plasma that affects our magnetosphere carries information about processes that occurred when the comet was millions of kilometers closer to the Sun, demonstrating the role of the solar wind as a communication medium throughout the heliosphere. The third irony emerges from the detection methods required. The most sophisticated space-based instruments struggle to identify clearly the subtle signatures of comet wake encounters. While Earth's own magnetic field serves as a natural detector capable of recording these interactions through changes in global electromagnetic phenomena, our planet's magnetosphere functions as a sensitive plasma physics instrument on a planetary scale. As Earth continues its orbital motion, the encounter with the comet's wake gradually concludes, and normal solar wind conditions return to our planet's magnetospheric environment. The transient modifications to radiation belt populations, auroral activity, and ionospheric dynamics fade as the terrestrial electromagnetic system relaxes back toward its equilibrium state. Yet the encounter leaves behind subtle changes in the composition of Earth's radiation belt populations, as some ions of interstellar origin may remain trapped in the magnetosphere for extended periods. These particles serve as long-term tracers of the comet's passage through our solar system, preserving samples of alien matter within Earth's own electromagnetic domain. The magnetospheric encounter thus represents a form of interstellar matter exchange, where materials that formed around distant stars billions of years ago become temporarily incorporated into Earth's plasma environment. This exchange occurs on scales too small to affect terrestrial processes directly, but large enough to provide scientists with opportunities to study the composition and properties of matter from other stellar systems using Earth-based facilities and techniques. Interplanetary dust detectors aboard spacecraft scattered throughout the solar system begin registering the microscopic debris trail left by our interstellar visitor as it approached, past perihelion, and departed toward the outer darkness. These instruments, designed to measure the flux and properties of dust particles permeating interplanetary space, encounter grains of alien matter that carry within their crystalline structure the chemical and isotopic signatures of materials formed around another star billions of years ago. The detection process unfolds gradually over many months, as dust particles released from the comet's nucleus during different phases of its solar system transit spread along the visitor's orbital path. The smallest particles, accelerated to high velocities by solar radiation pressure, travel fastest and arrive first at spacecraft detector arrays. Larger particles follow more slowly, creating a temporal sequence of detections that encodes information about the size distribution and ejection velocities of material lost from the comet's surface. Each particle impact on a spacecraft detector creates a brief but intense plasma flash as the high-velocity grain vaporizes upon contact with the instrument's sensing surface. The properties of this plasma, its temperature, density, and elemental composition provide information about the impacting particle's mass, velocity, and chemical makeup. Advanced detectors can even distinguish isotopic ratios within individual dust grains, revealing details about nuclear processes in the comet's parent stellar system. The composition of the interstellar dust grains shows both similarities to and differences from solar system materials. Silicate minerals appear in familiar forms, olivine, pyroxene, and amorphous glass, but with isotopic ratios that mark their extrasolar origin. The ratio of oxygen-16 to oxygen-18, for example, differs measurably from values typical of solar system materials, reflecting different conditions in the stellar nebula where these grains originally condensed. Carbonaceous compounds within the dust particles display even more dramatic compositional differences, with complex organic molecules that may have formed through radiation processing during the comet's long journey through interstellar space. These organic compounds include species rarely found in solar system materials, providing insights into the chemistry of carbon-bearing molecules under the extreme conditions of the interstellar medium. Crystalline structure analysis reveals that many of the dust grains preserve delicate mineral textures, indicating formation under conditions of slow cooling and minimal mechanical disruption. This preservation suggests that the comet's nucleus has experienced remarkably little heating or shock processing during its billion-year journey from its parent stellar system to our Sun. The spatial distribution of detected dust particles reflects the complex dynamics of particle ejection and subsequent evolution under solar radiation pressure. Particles detected in the inner solar system show evidence of substantial acceleration away from the Sun, while those encountered in the outer regions retain velocity vectors closer to the comet's original orbital motion. This spatial segregation creates opportunities for spacecraft at different heliocentric distances to sample different populations of dust particles from the same comet, providing a comprehensive view of the visitor's dust production and evolution processes. Near-Earth spacecraft encounter primarily the smallest, fastest-moving particles, while missions in the outer solar system detect larger, slower-moving grains that retain more information about conditions on the comet's surface. The temporal evolution of dust detection rates reflects the varying intensity of dust production throughout the comet's solar system passage. Peak detection rates occur several months after the comet's perihelion, as particles ejected during maximum activity reach the orbital distances where sensitive detectors are located. Lower but persistent detection rates continue for years, as larger particles gradually spread throughout the inner solar system. The mystery of dust grain survival during high-velocity impacts on spacecraft detectors presents ongoing challenges for instrument design and data interpretation. The extreme conditions created during impact, temperatures exceeding those found in stellar atmospheres, pressures rivaling those in planetary cores, can alter or destroy the very properties that scientists seek to measure. Advanced detector designs attempt to minimize these destructive effects by using glancing angle impacts or capture techniques that decelerate particles more gently. Even so, much of the detailed structural and compositional information contained in dust grains is inevitably lost during the detection process, limiting the precision with which interstellar materials can be characterized. The flux rates of interstellar dust particles detected throughout the solar system provide constraints on models of the comet's total mass loss during its passage through the inner regions. Integration of particle flux measurements over the appropriate spatial and temporal scales suggests that the visitor lost approximately 1 million tons of material during its solar system transit, a small fraction of its total mass, but enough to create detectable signatures throughout interplanetary space. The first irony of dust detection emerges from the scale of the phenomenon. Particles measuring micrometers across, individually invisible to the most powerful optical telescopes, create detectable signals when they impact spacecraft traveling at velocities of tens of kilometers per second. The extreme conditions of the impact transform invisibly small grains into brief but measurable plasma events. The second irony lies in the information content. The destructive process of high-velocity impact that vaporizes dust particles completely also provides the only practical method for analyzing their composition and structure. The act of detection necessarily destroys the object being studied, requiring sophisticated techniques to extract maximum information from each brief impact event. The third irony becomes apparent through consideration of the detection timescales. Dust particles that required millions of years to travel from their parent stellar system to our solar system are detected and analyzed in microseconds during spacecraft encounters. The entire scientific return from these ancient travelers is compressed into measurement intervals shorter than human reaction times. Some dust particles follow trajectories that carry them beyond the heliopause and back into interstellar space, where they will continue their journey among the stars for millions of additional years. These particles now carry within their structure subtle modifications imposed by solar heating and charged particle bombardment, serving as inadvertent probes of conditions within our solar system's plasma environment. Other particles become trapped within the solar system's gravitational well, joining the population of interplanetary dust that contributes to zodiacal light and provides raw material for planetary, atmospheric phenomena. These grains of interstellar matter become permanently incorporated into our solar system's inventory of solid materials, adding their microscopic contribution to the complex mixture of dust that fills the space between planets. The detection of interstellar dust particles thus provides both a scientific opportunity and a demonstration of the interconnected nature of matter throughout the galaxy. Materials that condense from the gaseous envelope of a dying star eventually find their way into the sensors of human-built spacecraft, bridging the vast scales of space and time that separate stellar death from technological detection. As spacecraft continue their missions throughout the solar system, dust detectors remain alert for additional encounters with particles from the comet's debris trail. These continued detections will extend over many years, as the largest and slowest moving particles gradually disperse throughout the heliosphere and contribute to the ongoing evolution of our solar system's dust environment. The corridor gradually heals with the inexorable patience of fluid dynamics operating on cosmic scales, as undisturbed solar wind slowly flows inward to fill the cavity carved by our interstellar visitors' passage through the inner heliosphere. This healing process unfolds over timescales measured in years rather than months, demonstrating the persistent nature of large-scale modifications to the solar wind's structure and the complex physics governing plasma flow in the space between planets. The restoration begins at the edges of the disturbed region, where the boundaries between modified and normal solar wind create pressure gradients that drive plasma motion toward the cavity's interior. Solar wind flowing around the edges of the wake region gradually converges toward the central axis. But this convergence must overcome magnetic pressure effects and plasma instabilities that resist the healing process. Magnetic field lines threading the cavity region retain their twisted, reconnected configurations long after the comet's departure, creating electromagnetic forces that oppose the inward flow of new plasma. These field lines, stretched and tangled by their interaction with the visitor's magnetosphere, slowly relax toward lower energy states through a series of reconnection events that release stored magnetic energy and accelerate particles to high velocities. The three-dimensional structure of the healing process reflects the complex geometry of the original disturbance, with different regions of the cavity filling at different rates depending on their magnetic field topology and distance from the wake boundaries, near the wake's central axis, where the comet's influence was strongest. Healing proceeds most slowly as plasma must overcome the greatest magnetic pressure barriers. Toward the wake's periphery, normal solar wind conditions return more rapidly as diffusion processes smooth out the gradients in plasma density and magnetic field strength. The result is a gradual shrinking of the disturbed region, with boundaries that become less distinct over time as the sharp transitions between modified and normal plasma give way to broader transition zones. Within the shrinking cavity, residual populations of pickup ions continue to influence local plasma properties through their interactions with the inflowing solar wind. These ions, created through ionization of neutral comet material during the visitor's earlier passage, carry distinctive velocity distributions and chemical signatures that mark their origin in materials formed around another star. The pickup ion populations undergo gradual dilution as normal solar wind plasma mixes with the cavity contents, but some signatures of the interstellar visitor persist for years in the form of isotopic and chemical anomalies detectable by sensitive mass spectrometers. These anomalies serve as long-term traces of the comet's passage, preserving information about both the visitor's composition and the plasma physics processes that governed its interaction with the solar wind. Plasma waves generated during the original comet-solar wind interaction continue to propagate throughout the healing cavity, carrying energy and momentum between different regions and facilitating the mixing processes that gradually restore uniform conditions. These waves, with frequencies ranging from the ion cyclotron frequency to much lower magnetohydrodynamic modes, create a complex electromagnetic environment that influences particle motion and energy transport throughout the region. The temporal evolution of the healing process shows multiple characteristic timescales that reflect different physical mechanisms. Short-term variations, occurring over days to weeks, reflect the arrival of new solar wind plasma with different properties due to variations in solar activity. Intermediate-term changes, spanning months, correspond to the gradual redistribution of magnetic flux and the relaxation of field line configurations toward minimum energy states. Long-term evolution, extending over years, involves the complete restoration of normal plasma flow patterns and the final dissipation of electromagnetic structures created by the comet's passage. This longest timescale reflects the fundamental challenge of removing magnetic field perturbations from a conducting plasma, where field lines cannot simply disappear, but must instead undergo complex topological changes through reconnection processes. The mystery of cavity healing rates remains an active area of theoretical and observational research in heliospheric physics. Computer simulations suggest that complete restoration of undisturbed conditions may require several solar rotation periods, during which time the cavity experiences multiple encounters with different solar wind streams carrying varying magnetic field orientations and plasma properties. Observational verification of healing timescales presents significant challenges, as few spacecraft maintain positions that allow long-term monitoring of specific regions in the solar wind. Most available data comes from statistical studies of many different plasma disturbances, making it difficult to track the evolution of individual cavities created by comet passages. The healing process also influences the propagation of solar energetic particles through the affected region, as the gradually changing magnetic field configurations create time-varying pathways for high-energy proton and electron transport. Particles accelerated by solar flares encounter evolving scattering centers and magnetic field irregularities that modify their trajectories, in ways that depend on the healing stage. These particle transport effects contribute to space weather phenomena throughout the inner solar system, as energetic particles that would normally follow predictable paths along magnetic field lines experience additional scattering and deflection while passing through regions undergoing cavity healing. The resulting modifications to particle arrival times and intensity distributions create subtle but measurable changes in radiation environments around planets and spacecraft. The first irony of the healing process emerges from its relationship to the original disturbance. The most persistent signature of the comet's passage through our solar system consists of empty space gradually being refilled with normal solar wind plasma. The visitor's most lasting impact involves the absence of material rather than its presence, demonstrating how gravitational and electromagnetic interactions can create large-scale voids in cosmic plasma flows. The second irony lies in the information preservation. As the cavity heals and normal conditions return, detailed information about the comet-solar wind interaction becomes encoded in the statistical properties of plasma turbulence and magnetic field fluctuations throughout the region. This information persists in forms too subtle for direct observation, but potentially recoverable through sophisticated analysis of plasma wave spectra and particle distribution functions. The third irony becomes apparent through consideration of the global context. While the cavity healing represents a local restoration of normal solar wind conditions, the process simultaneously contributes to the overall heating and acceleration of the solar wind as it flows outward through the heliosphere. Magnetic reconnection events and plasma wave interactions associated with healing dissipate energy and momentum in ways that influence bulk solar wind properties far from the original disturbance site. As the healing progresses, the cavity's boundaries become increasingly difficult to define, as sharp gradients in plasma properties give way to broader transition regions where modified and normal solar wind gradually blend together. This boundary diffusion represents the final stage of the healing process, where the last traces of the comet's influence fade into the background turbulence of the normal solar wind. The magnetic field strength within the healing cavity gradually decreases toward normal values as reconnection processes release the enhanced field compression created during the comet's passage. This magnetic pressure reduction allows solar wind plasma to flow more freely into the cavity interior, accelerating the final stages of density and temperature equilibration. Plasma instabilities associated with the healing process create enhanced levels of electromagnetic wave activity throughout the affected region, contributing to local heating of the solar wind plasma and acceleration of particles to suprathermal energies. These effects, while localized to the cavity region, influence the overall energy balance of the solar wind flow and contribute to the gradual heating observed as solar wind plasma propagates outward through the heliosphere. The dust particles left behind by the comet's passage continue to influence the healing process through their interactions with the inflowing solar wind plasma. Charging effects and grain impacts create localized plasma perturbations that contribute to the overall electromagnetic environment within the cavity. While the gradual dispersal of dust throughout the region provides traces for studying plasma flow patterns during healing, some magnetic field lines retain their connection to the original comet interaction region throughout the healing process, creating persistent channels for energy and particle transport between the cavity and the broader heliosphere. These connected field lines serve as conduits for continued influence of the healing process on plasma conditions at distant locations throughout the solar system. The cavity healing thus represents not simply a return to pre-existing conditions, but rather a complex evolution toward a new equilibrium state that incorporates the permanent modifications to heliospheric structure created by the interstellar visitor's passage. The solar wind that eventually fills the healed cavity carries within its plasma properties subtle signatures of the interaction processes that originally created the disturbance. As years pass and the healing approaches completion, the region of space once dominated by the comet's plasma environment gradually becomes indistinguishable from the surrounding solar wind. Yet even in this final state, sensitive instruments might detect traces of the ancient encounter in the form of isotopic anomalies, magnetic field irregularities, and particle population characteristics that preserve the memory of an alien visitor's brief passage through our stellar domain. Return to deep space beckons with the inevitability of celestial mechanics. As our interstellar visitor crosses beyond Neptune's orbit and begins its final departure from the gravitational embrace of our Sun. The same mathematical precision that governed its approach now dictates its recession, carrying the ancient wanderer back toward the cold realm between stars, where it will resume the billion-year journey that brought it briefly into our domain. The comet's nucleus, now reduced in mass by the million tons of material lost during its passage through the inner solar system, continues its steady recession from the Sun along a hyperbolic trajectory that will carry it beyond the heliopause and into the local interstellar cloud. Its surface temperature drops steadily as solar heating diminishes according to the inverse square law, and the sublimation processes that created spectacular plasma phenomena during perihelion passage gradually subside toward the minimal levels that sustained the comet during its long approach. Behind the departing visitor stretches the wake, that vast corridor of modified solar wind that extends across astronomical units of space and will persist for years after the comet itself has vanished beyond the range of human telescopes. This wake serves as the most enduring signature of the encounter, a temporary modification to heliospheric structure that demonstrates how even small objects can reshape the large-scale plasma environment of an entire stellar system. The plasma cavity carved by the comet's interaction with the solar wind begins its slow healing process as undisturbed solar wind gradually flows inward to fill the evacuated regions. This healing unfolds with the characteristic timescales of magnetohydrodynamic processes operating over interplanetary distances, months to years for complete restoration of normal plasma flow patterns and magnetic field configurations. Within the healing cavity, populations of pickup ions created during the comet's active phase continue to provide signatures of the interaction long after direct outgassing from the nucleus has ceased. These ions, bearing the chemical and isotopic fingerprints of materials formed around another star, become gradually diluted by the inflowing solar wind but retain their distinctive properties for extended periods. The dust trail left by the visitor's passage creates its own persistent structure throughout the inner solar system, as particles of different sizes follow trajectories determined by their responses to solar radiation pressure and planetary gravitational perturbations. The smallest particles, accelerated to high velocities, rapidly disperse throughout interplanetary space and contribute to the zodiacal dust cloud. Larger particles remain concentrated along the comet's orbital path, creating a debris trail that spacecraft may encounter for decades. The temporary reshaping of local space-time achieved during the comet's passage represents a remarkable demonstration of how gravitational and electromagnetic forces can create large-scale structures from the interaction of relatively small masses with their plasma environment. The visitor's influence extended across spatial scales millions of times larger than its physical dimensions, affecting plasma processes throughout a volume of space comparable to the inner solar system itself. The mystery of the comet's ultimate destination deepens as astronomers attempt to predict its trajectory through interstellar space. Gravitational perturbations from the giant planets have modified its velocity by several kilometers per second, altering both its speed and direction relative to its approach trajectory. These changes will influence which stellar systems the visitor might encounter during its continued journey through the galaxy. Current calculations suggest that the comet will take approximately 40,000 years to travel beyond the Sun's sphere of gravitational influence and enter the realm where other stars begin to exert comparable attractions. During this time, it will gradually cool toward the temperature of the cosmic microwave background, eventually reaching thermal equilibrium with the radiation environment of deep space. The isotopic and chemical modifications imposed by solar heating and charged particle bombardment during the comet's solar system passage will permanently alter its surface composition, adding solar wind elements to materials that originally formed around another star. These modifications, while subtle, create a permanent record of the visitor's encounter with our stellar environment. The electromagnetic disturbances propagated throughout the heliosphere by the comet's interaction with the solar wind carry information about both the visitor's properties and the structure of our solar system's plasma environment toward the heliopause and beyond. These disturbances, traveling at characteristic speeds of hundreds of kilometers per second, will reach the boundary between our solar system and the interstellar medium years after the comet's departure. The first irony of the visitor's departure lies in its enhanced visibility during recession, while the comet becomes increasingly difficult to observe as its distance from the Sun increases. The wake structures it created during approach and perihelion passage continue to provide detectable signatures of its presence throughout the heliosphere. The second irony emerges from the trajectory modifications. Gravitational interactions with our solar system's planets have changed the comet's path through interstellar space, potentially directing it towards stellar encounters that would not have occurred without its brief passage through our domain. Our solar system thus serves as a gravitational lens that redirects interstellar objects toward new destinations among the stars. The third irony becomes apparent through consideration of the information exchange. While the visitor carries away isotopic and chemical signatures of our solar system's plasma environment, it leaves behind traces of its own alien chemistry in the form of dust particles and ion populations that will persist throughout the heliosphere for years or decades. As the comet crosses the orbit of Pluto and approaches the heliopause, its interaction with the solar wind gradually weakens as plasma densities drop and magnetic field strengths diminish. The bow shock that characterized its passage through the inner solar system eventually disappears as the comet's atmosphere becomes too tenuous to create significant disturbances in the increasingly rarefied plasma environment. The ion tail, once extending across millions of kilometers of space, gradually dissipates as photoionization rates decrease and magnetic field line tension weakens. The dust tail persists longer, as solid particles continue their ballistic trajectories under the influence of solar radiation pressure, but eventually disperses as particles spread throughout the heliosphere or escape entirely from the solar system. The final traces of plasma interaction occur as the visitor approaches the termination shock, where the solar wind encounters the interstellar medium and begins its deceleration towards subsonic velocities. Here, in the boundary region between our solar system and interstellar space, the last signatures of the comet's electromagnetic influence merge with the complex plasma phenomena that characterize the heliosphere's outer limits. Beyond the heliopause, the visitor will resume its journey through the local interstellar cloud, carrying within its modified surface layers a record of its encounter with our young and active star. This record, encoded in isotopic ratios and chemical compositions altered by solar wind bombardment, will persist throughout the comet's continued travels among the stars. The temporary reshaping of space-time around our visitor reaches its conclusion as normal plasma flow patterns gradually return throughout the affected regions of the heliosphere. Yet the memory of the encounter persists in subtle modifications to heliospheric structure, particle populations, and magnetic field configurations that will influence solar wind dynamics for years after the comet's disappearance into interstellar darkness. The solar wind flows onward through the vast emptiness between worlds, carrying within its streaming plasma the fading signatures of an ancient encounter, where once a visitor from another stellar system carved corridors through the flowing particles and bent magnetic field lines into complex geometries. Now, only gentle variations in density and temperature mark the healing wounds in space-time itself. across the millions of cubic kilometers where plasma cavities slowly fill with undisturbed solar wind. The memory of alien chemistry gradually dilutes into the background composition of our star's extended atmosphere. Pick up ions bearing isotopic ratios from a stellar system that died before Earth formed. Continue their gyrations around magnetic field lines, but their distinctive signatures fade with each passing solar rotation as normal plasma conditions slowly return. The dust particles, those microscopic messengers carrying crystalline records of conditions around distant stars, continue their ballistic journeys through interplanetary space with the patience of geological time. Some will eventually impact planetary atmospheres, adding their infinitesimal contribution to the cosmic dust that falls continuously on all worlds. Others will escape the solar system entirely, resuming journeys that may last millions of years before encountering another stellar system. Behind the departing visitor, magnetic field lines gradually relax toward configurations of minimum energy, releasing in small increments the vast amounts of electromagnetic energy stored during the plasma interactions of perihelion passage. These energy releases, occurring through reconnection events and plasma wave dissipation, contribute to the overall heating of the solar wind as it expands outward through the heliosphere. The wake region, once clearly defined by sharp boundaries between disturbed and normal plasma, slowly loses its distinct identity as diffusion processes smooth away the gradients that mark the passage of our interstellar guest. Yet even as these boundaries fade, subtle statistical signatures persist in the turbulence spectra and particle distribution functions throughout the affected volume of space. In the cold realm beyond Neptune, where sunlight becomes indistinguishable from starlight and plasma densities approach those of the interstellar medium itself, the last traces of electromagnetic interaction fade into silence. The visitor resumes the ancient rhythm of its journey between stars, carrying within its nucleus both the pristine chemistry of its birth around another sun and the subtle modifications imposed by its brief passage through our domain. The corridors carved through the solar wind will eventually heal completely, leaving no trace of the temporary reshaping that affected plasma flow patterns across astronomical scales of space. Yet the encounter itself joins the long history of such meetings between wandering worlds, demonstrations of the dynamic connectivity that links stellar systems across the galaxy through the medium of gravitational forces and electromagnetic fields. The solar wind continues its eternal expansion toward the heliopause and beyond, where it will eventually merge with the interstellar medium and contribute its processed elements to the galactic reservoir of matter from which future stars and worlds will form. Within that flow moves the diluted essence of our visitor's passage, atoms that condensed from the death breath of alien stars, now dissolved into the life stream of our own.